So hi everyone. Yeah, again, apologies for the various technical difficulties on my end. But yeah, I'm Pratyush, and I'll be talking about Arkworks, which is our Rust ecosystem for snarks. This is the collaborative effort of a lot of people at Berkeley, as well as a number of external contributors. So you can go to Arkworks.rs to sort of look at our GitHub repo. So this, I guess, event has been more about sort of the a showcase of the different languages. But Arkworks, it has a framework to write constraints for snarks, but also has sort of APIs and libraries for basically every level of the sort of snark stack. So including algebraic stuff, implementations of snarks themselves, and then gadgets and constraint writing frameworks. And then applications built on top of those, all of these things, such as implementation of zkSessions and proof-trying data and more. So in a little bit more detail. So the bottom level of the stack, you have the very core algebraic objects such as fields and elliptic curves and polynomials and efficient algorithms or all of these. We abstract all of these away behind a generic API, so that at the next level of the stack, which is describing or implementing actual snarks, you don't have to worry about the details of your underlying curve implementation or field implementation. You can just be generic over the corresponding trait. And then we sort of have a corresponding chain system API that you can use to program circuits for these snarks. And using this generic API, we implement a number of cool gadgets for everyday programming, as well as for useful cryptographic primitives. And then we use these inside Arkworks to implement some cool applications, and external folks have also used it. So for example, Cello uses our constraint writing framework to for their circuit of like batch verification of BLS signatures. Yeah, but in this talk, we'll focus primarily on how you would actually do application development with Arkworks, and we'll mainly focus on the constraint writing portion. So if you want to write your own cool snark application, right? There's two components. You have to decide what kind of snark you want to use, as well as you have to express your application logic in some form that is understandable by the snark, right? So for the first choice, you have to decide what snark you want to use, and you have to decide what curve you want to use with that snark. For the second thing, you have to use these existing gadgets, or maybe write your own gadgets to express your logic. So let's delve into each of these steps in a little bit more detail. So for choosing a snark and a curve, as you saw earlier, we have these very generic APIs that you can use to we have a generic snark trait and a generic curve trait, and you can sort of plug and play all the different various combinations as long as they're compatible. So in a little bit more detail, so let's say you have Grot16, right? And you want to switch between BLS 12377 to BW6 or any other pairing-friendly curve. To do that, all you need to do is just change one type parameter. You don't really have to do re-implement Grot16 at all. Similarly, if you want to switch between proof systems, you can be generic over the kind of proof system, and all you have to do is switch out the type parameter. So let's say you for some reason think that Grot16 doesn't provide enough simulation extractability or non-malleability. You can switch to Groth-Mahler, or now let's say you're tired of the burst circuit trusted setup, you can switch to Marlin, or in the future Plonk, just by changing one. And then let's say you want to switch from polynomial commitments within Marlin or within Plonk or any of these recent polynomial commitment-based snarks. Again, all you have to do is just switch out the type parameter from, for example, KZG10 to a bulletproof-based polynomial commitment like in Halo, right? So we make it easy to switch between snarks. But like, I guess this is like sort of the easy part. The tough part is actually expressing your constraints for your application in a way that's understandable by the snark. And we've already been over R1CS. I won't go into too much detail, but like the rough takeaway for R1CS is that it's a sort of mathematical way of expressing computation, which is understandable by snarks. But the problem is that humans are not very good at writing math directly. So you ideally want some sort of abstraction that allows you to write high-level stuff and that is human understandable and compiled onto R1CS. And to do that, we provide a very high-level and efficient constraint writing framework that it looks essentially like you're writing native code in Rust, but compiles down in the backend to something which looks like which is R1CS. Let's delve a little bit more deeper into this backend or into this framework. So we provide within this framework a number of useful gadgets. So if you want to do standard programming, such as want to have conditional selection or with Booleans or add unsigned integers and so on, we have tools for that. We also have gadgets for algebraic objects such as elliptic curves and finite fields. And then you can use both of these components together to reuse it to implement useful cryptographic primitives such as hash functions of various kinds, signature verifiers, Merkle tree verifiers, recursive snark verifiers. And all of these are implemented right now in our libraries. And yeah, you can use these APIs to implement your own higher level primitives or to implement your application logic. So let's take a look at how you would actually use these objects, right? And we'll do this via this example of Kurotsuba multiplication. So at the top you have this Kurotsuba multiplication algorithm is some algorithm that is used within I guess Snark development. So it's not really, you don't really have to worry about too much what it does. But basically at the top you have the native Rust code, which is what you would execute on your computer normally. And at the bottom you have something which is left from the previous version of Arkworks, which is very similar to Bellman. But this is how you sort of express that logic in the sort of this older style of writing constraints. As you can see, it sort of completely obscures the logic like the logic flow which is happening in the top code sample, right? It's very difficult to match the two and see which part corresponds to what. So to resolve that, in sort of our latest version of Arkworks, we changed our APIs and introduced new abstractions, which allows us to use things like traits and overloading of operators to make the sort of native code almost match entirely with the constraint code, right? So there's only some Rust technicalities which make the two different, but otherwise it's very easy to sort of follow to compare the constraint code to the native code and make sure that the logic is implemented correctly, right? And sort of the same applies for we have very high level APIs which match the Rust code for something like a hash function to sort of this equivalent constraint code. And sort of that's a takeaway that with our library you can write these constraints in a manner that's very similar to how you would just write them for normal execution in Rust. So in comparison with like DSLs, there's some advantages and some disadvantages. So the pros are because you're just writing Rust, you can just leverage properties of Rust, which include the very strong type system and memory safety, and the great speed, and the great tooling such as Cargo and the sort of surrounding ecosystem of crates, right? You can also leverage non-determined. You can just compute the witness via normal Rust, and this leads to more efficient circuits. Some DSLs, I think most DSLs that we've seen today, they don't directly allow the end user to leverage non-determinism. And support for debugging and profiling circuits, which we have to actually improve a little bit, but it exists, and I'm not sure for existing DSLs it's quite there yet. The cons are that you have to learn Rust, which is probably much more complex than learning some very a simple DSL that's optimized for programming Snarks. And on top of that, you have to learn how to use our framework and the sort of surrounding APIs. But hopefully that's not too much of overhead. And we're still sort of working out how to be compatible with other ecosystems. So you write your constraints in Arkworks and they plug them into some of the other proven backends that we saw today, like Aztec or Halo 2 or so on, right? Via zk interface, but you might sacrifice some efficiency by doing that. And I want to sort of note that you can use the rest of the Arkworks, not everything below the constraint writing stack, as a backend for a DSL. And as you saw earlier already, Socrates has already integrated this. Noah, I think there are plans or in-progress plans to implement this, and Leo as well. I think there is a sort of in-progress plan to do that. So yeah, your DSL could easily support Arkworks as the proof systems in Arkworks as a backend. Okay, yeah, so that's it. There's a number of contributors both at Berkeley as well as externally with all kinds of experience levels. We have a number of stars in all of our repos. If you want to get started with Arkworks, these are sort of the relevant links. The GitHub and the Twitter. There's also a Telegram. And recently at the ZK Proof workshop, I gave a tutorial on actually using our framework to do a simple roll-up style application. You can take a look at that to become familiar with the ecosystem. Thank you.